Hi, my name is Raghu Govindachari. The whole revolution of the RISC architectures is based on the power of the modern compiler technology. Much of the execution time reduction for code is achieved by the compiler using a wider set of registers, analyzing of dependencies, and reducing loads and stores. Further, compilers can analyze loops and function calls to remove invariants, reduce loading globals and statics, and even entirely removing function calls. They can reorder execution of high-level language statements to reduce loads and stores. Finally, they can judiciously use machine instructions for a given computation and also schedule them to minimize pipeline stalls or maximize parallelism. In this video, we will look at some of the optimization techniques and also how to make better use of them while writing readable, maintainable C code. It is often assumed that embedded systems programming always implied using coding tricks to make execution faster or reduce code size. That was definitely true with older 8-bit and 16-bit MCUs, where substantial coding was in assembly language to directly exploit the MCU's capabilities. With the advent of 32-bit MCUs and modern compilers, the onus of doing that has shifted from the software developer to the compiler. The first and foremost duty of the software developer is to write readable and maintainable code. Take a look at the code shown here. It is a correct but somewhat cryptic code for debouncing a switch. It's not immediately obvious how it achieves debouncing and whether correctly. While the programmer can take pride in such code, after proving that it works, it's not worth the effort later to maintain it. An optimizing compiler tries to generate code that is both small and fast. It does so by repeatedly applying a number of transformations to the source program. Most optimizations follow mathematical or logical rules based on a sound theoretical foundation. Other transformations are based on heuristics, where experience has shown that some transformations often result in good code or open up opportunities for further optimization. There are very few cases where the optimizer relies on black magic, so the way you write your source code can determine whether an optimization can be applied to your program or not. Sometimes small changes in the source code can have a significant impact on how efficient code the compiler can generate. Trying to write your code on as few lines as possible using arcane facets of the language, post increments, and comma expressions to squeeze in a lot of side effects in a single expression will not make the compiler generate more efficient code. It will just make your source code convoluted and hard to maintain. It's easy to overlook a post increment or an assignment if it is done in the middle of a complex expression. Why write code in a style that is not easy to read, while the compiler can still generate efficient code? Compiler does its optimization in multiple stages. There are two parts to the compiler, the front end and the back end. The front end deals with the lexical analysis and syntactic analysis of the code, and then the back end is involved in the code generation. That is where all the optimization stages are. So the compiler backend is divided into 5 stages as shown in this figure. Optimization, in fact, occurs at each stage, although global optimization is the most important. The global optimizer performs both high-level program analysis and a wide range of general optimizations. These general optimizations are database driven, so they can be tuned to a particular architecture. For example, the global optimizer uses the database to determine the number of registers available for a particular architecture. The code selection and generation process utilize the same database as the global optimizer to determine the optimal assembly language instructions to implement the intermediate language operations. The code selection process reserves a number of registers for use as scratch pads for temporary variables. The prime purpose of the code generator is to finalize register usage by ensuring that any unused scratch registers are utilized for storing variables that would otherwise have to be fetched from memory. Once registers usage has been finalized, the dependencies between instructions become clear. This sets the stage for the peephole optimizer, which initially performs obvious elimination, in which it scans the generated code for clearly inefficient sequences. However, its primary purpose is instruction rescheduling, which reduces the potential for runtime pipeline stalls. With the latest CISC processors themselves becoming more RISC-like, and with market pressure for faster, denser code, a new class of compiler optimization techniques have emerged. In many cases, these new optimizations involve sophisticated program analysis techniques that have greatly broadened the scope for applying well-established optimizations such as a constant or copy propagation. In effect, these new analysis techniques enable the compiler to critique high-level C or C++ source code in order to combine optimizations more judiciously for maximum effect. Some of the advanced optimization techniques include interprocedural analysis, live analysis of global and static variables, profile-driven optimization, function inlining, and complex branch optimization. We will look at some of them in detail. Let's look at a simple example of how the source code has an impact on what the compiler generates in the object code. So here is two versions of computing a factorial. Mathematically, they are identical. It's a product of a sequence of numbers from 1 to n. Since multiplication is commutative, one can do the multiplication starting with 1 and ending with n, or you can start with n and end with 1. So functionally, they are equivalent. Apparently, they seem to be having no difference in terms of extra operations. So are they same? Let's have a look. Usually, decrementing loops, that is the one on the right side, happen to generate better code. Why? This is because there is in the assembly code there'll be a branch back based on a comparison of the loop termination condition. On the left hand side, there are two variables, I and n, in the comparison operation, I less than or equal to n. Now, on the right hand side, there is a comparison with 0, where I is not equal to 0. Therefore, it seems the compiler can generate efficient code by avoiding one comparison operation. For decrementing loop, we can see that the subtract operation on the iterator I will be followed by a branch, a conditional branch on comparison with 0 or not 0. So if it is branch on not 0, loop back. So there is no actual comparison. It is using a conditional instruction, which we saw in the MCU instruction set. So just after the subtraction, the 0 bit of the conditional flags would be set, and that can be used in a conditional equation to do the loop back. So it has reduced one comparison operation. Is it a big deal? Maybe not for this small one. However, imagine having a loop which iterates millions of times or thousands of times. One instruction saved is significant when the number of iterations is very high. Let's look at that in let's look at that in the disassembled code generated by the actual compiler. Here is a source code of the program that computes factorial in two different ways. As you can see, the main function is calling two versions of factorial, fact1 and fact2, where fact1 is using an incrementing loop. So the termination condition is I less than or equal to n, and fact2 is using a decrementing loop where the termination is I not equal to 0. Let's look at the disassembly code generated by the compiler with the medium optimization set. So here is at the top the function fact1, the code that implements this function. So there is initial uh, initializations, and then here is the actual multiplication inside the loop, followed by incrementing of the index. Subsequently, a comparison is made with the end condition, which is with n. So R1 and R2, or R2 is holding the index, R1 is holding the terminal value n. And if it is greater than or equal to, it loops back. And when it is equal, it's actually greater than or equal to, it will exit. So here is the second version, factorial 2. Initially it looks same. However, after the multiplication, there is a decrementing of the index followed by branch on not equal. This is a conditional execution. So there is no comparison operation. Like in the previous case, there is an add followed by comparison. Here there is a subtract followed by no comparison because it is uh, zero comparison against zero. It is implicit. So it is using the 0 bit of the condition register, and using the conditional execution, it avoids one explicit comparison operation. So that's the idea of how a simple transformation of the code can result in one less instruction in this case. But if the number of iterations in the loop is very high, it adds up. Inter-procedural analysis is an advanced optimization technique. It's typically used while a function call is being made to analyze whether what global data is being accessed by the function, what needs to be stored on the stack, which register needs to be preserved on the stack according to the ARM AAPCS convention, and which can be actually avoided from being stored. So that is one part of it. The second part is basically whether the call itself can be avoided and so on. So here is an example here where there is an array of 100 elements, and there are two variables C and D which are initialized to 100 and 10 respectively, and a function called bar is called, which iterates over 100 times and assigns a, the result of the function call foo to each of the array variables from 0 to 99. Now the foo itself does very little. It's just returning returning a by b, integer division of a by b, and the result is stored in array function. If you look at the optimization with the inter-procedural analysis, basically it can store the temp. So this function call is doing nothing but a by b in every time it is called, it can be stored in a temporary variable, a temp equal to c by d, and it can be used for assigning. Then there is also loop unrolling. Basically, it trades off the number of instructions with a branch overhead. So the original loop is 100 times. Here it is actually divided into 25 iterations with 4 different elements being assigned in each iteration. So this is typical loop unrolling. And so there are two effects here. The procedure analysis suggests that this function is not doing, and it's actually having an invariant value, which can be, so the whole function can be replaced by a temporary variable, which can be assigned to all the elements, and the assignment itself is done by unrolling the loop to 1/4. Basically, 4 statements, and the number of loops is 1/4. Here is the example code, which is basically the main function initializing two variables local variables c and d to 110 before calling the function bar. The function bar is iterating 100 times over all the elements of the array, uh, assigning each element with the return value from the call to the function foo. Function is called with parameters c and d. If you look at foo, basically it is doing the ratio of the first parameter to the second parameter. Now here is the disassembled code. So it starts with initializing C to 100 and D to 10. After that, there is the index variable which is stored in register R2. You can see that it's the limit of the limit of the iteration is now 25 instead of 100. That means it's 1/4 of the loop termination value. Correspondingly, 4 different elements are assigned. You can see 4 store operations with offsets 0, 4, 8, and 12. So 4, each is a 32-bit address. So you can see that 4 array elements are being assigned values. The interesting thing is, if you see here, there is no function call to the function foo. The ratio c by d was computed, and that value is stored in R0, which is stored in each of the array elements directly. So there are 2 things that have happened. One is that the computation of c by d has actually 3 things have happened. The ratio of c by d is computed directly. You don't even see a division operation. That's because C and D values are known at compile time. These are basically, this is called constant folding. So that the ratio C by D is computed at compile time. So there are no instructions generated for division. That is one optimization. That's called constant folding. The second operation is basically in terms of loop being, second optimization is in terms of the function call to foo has been replaced by the ratio c by d, which is stored in register R0, which is basically like a temporary variable. And then the third optimization is loop unrolling, where the loop iterations are being reduced to 1/4, and in each iteration, 4 elements are being assigned. So this is a very typical transformation that the compiler can do. A loop unrolling is always dependent on the trade-offs between execution time saved due to avoiding branching in the loop versus the number of repeated instructions that you have to include. So if here the compiler setting has been set for a balance, so balance between code size and execution speed. So it has made a decision to fold it 1/4. Let's now look at the third technique called live variable analysis. Basically, programs written for 8 and 16-bit architectures often make extensive use of global and static variables rather than local variables. This was done for performance reasons because such architectures typically provide a very limited number of registers. Unfortunately, when such code is executed on today's register-rich architectures, it may substantially decrease performance by forcing the processor to access memory every time it reads or updates a variable which is in the memory. One solution is to rewrite such code while porting to 32-bit processors, but most developers would prefer not to modify already working code, especially if the original programmer is no longer available. A better alternative is using the compiler to solve this problem. Live variable analysis enables the compiler to determine which variables should be placed in registers. Although frequently used by compilers with local variables, Performing such analysis for static and global variables is much more difficult. In particular, it is essential for the compiler to have sophisticated alias analysis. Alias analysis determines which variables are currently referenced by pointers, as illustrated by the following the code segment shown here. In the code segment, the static variables are x, y, and z. There is a pointer variable, which is a local variable, which is an alias for the global or static variable x. And then instead of using x, only the alias is used in the computation sequence here. You can see that z, which is a static variable, is frequently accessed. Okay, and so let's see what live variable analysis and alias analysis will result in when your compiler is optimizing it. So first thing is that it introduces a temporary register variable. This is not exactly a C code, handwritten C code. This is the logic that the compiler will generate in the assembly code. So there is a register variable, which is a temporary store, where the static variable is copied, and that copy is used in the computations rather than accessing the variable y, which is in memory every time. So once it is coming to the register, that register alone will be used. In order to update the value of z, so there are multiple assignment statements here for z. There is z equal to y is equal to z plus 45, and then finally uh, x minus z. Now, the compiler is smart enough to know that this is actually not, we will see how the compiler optimizes in the actual disassembly code. The first point of live variable analysis is to use a temporary variable, which is in register, rather than fetching every time from the memory. So here is the main program, which has three static variables x, y, and z, initialized to 0, 1, and 2. You can see in the watch window this x, y, z with initial values 0, 1, and 2, and they are at location 2000 hex 000, 4, and 8, and their type is integers. Then you have the assignment statements. Now here the pointer p is initialized to address of the static variable x. So p is an alias for x. As you can see in the code, only star p is used. X itself is not used. Now, this is disassembly code. First thing is that this computation 4 times j is done. So z equal to y is not done yet. So it is one of the optimization techniques is reordering of instructions within a short sequence of code or short block of code. This is to improve the register usage. So the compiler has done this. It is not computed this assignment z equal to y, but it has gone to the next one, which is alias for x equal to 4 times 123. And that it does in an interesting way by not using a multiplication operation, but by loading the value 246 and multiplying it by 2 using the logical shift left operation. Now the value is whatever 492. If we execute, we can see that it will be stored in the address pointed to by R0. Let's just execute that. So you can see the value variable x now showing value 492. Now it's subtracting 45 from this variable, which is star p, that is corresponding to this operation. Interestingly, it did not do an addition z equal to z plus 45. It did not do that. Instead, it is directly optimizing this sub expression. So star p minus z, if you subtract, so there will be subtracting by 45, and it has not done this z equal to y. So actually, if you see unoptimized code, it would have loaded z equal to 1, then it would have computed 46, and then it will subtract 46. But the compiler here has not done this assignment 1. It is subtracting this 45, and basically it is eliminating sub expressions here. So now you can see that it has subtracted 46 from 492 and stores it in. So this store operation is storing it in address 2000 which is nothing but Z. So multiple things going on here. One, there is a there is a constant uh, computation here, followed by the aliasing, followed by reordering of instruction sequence, and then common sub-expression elimination by computing this subtraction and storing the z value only the final stage. So there is no load and store operations except for the initial load and then the final store here. So this is basically the concept of live variable analysis. So the whole thing is centered around the avoiding the load and store operations as much as possible, reordering the reordering the sequence of execution, and therefore to not disturb the registers, and in the process also common sub expression elimination. The next optimization technique is called function inlining. The idea is to place a function call with the body of the function itself, just like a macro does at the preprocessor stage. Now, there are two implications. One is that it avoids the function calling overhead, basically saving the context, because ARM procedure calling standard expects the caller function to preserve certain registers which may be reused in the called function. So that is one overhead, and of course, upon return, it has to pop them back. That's a significant overhead. So if the function call itself is avoided, this context saving can be avoided as well. Now this works fine if the called function is not very big, like in the case of this swap function here, it just does two assignments here. And if the number of times this swap function is called is too much in the main application, then the code size will bloat that many times. So it has to be used judiciously, and all it does is basically avoid the function call overhead. Let's look at this code here. So this is equivalent to this function call is the x and y are the global variables with which it is called. So it is basically these two operations are directly inlined and there is no function call. So this is the transformation that happens here. So an additional advantage is that placing the function code inline exposes it to further optimization, uh, such as enhancing performance and more. So here is the same code of a main function calling swap, and here is the swap function's implementation. Let's look at what the optimizer can be set to. So we have chosen the highest level of optimization with only function inlining selected. Now let's compile this. So it's compiled. Let's load it. And here is basically the disassembly code, and these are the variables which are initialized x equal to 2 and y equal to 5 there in the watch variable window at address 0 and 4. Here is the function, main function. As you can see, there is no call to swap here. So the registers are loaded with the values, and then a move operation. So basically, the store operation directly handles the swap. Let's execute this, and so you can see that the value have been exchanged. So the idea is that the function call is completely eliminated, even though this is a corresponding source code here. The target code does not have a function call, which is a branch and link instruction. You instead see directly the load and store operations, which basically accomplishes the swap operation. So we saw the swap function being inlined out. Let's look at a slightly more complex uh, function. Here you have the main function calling uh, factorial fact1 with an argument unsigned value 3. So 3 factorial is what you want to compute. Here is the body of the function fact1, where it's basically just a typical downward counting loop, and the product is computed here and returned. Now, as you can see in the disassembly code, so the value 3 is loaded, but the function itself is not called. It is actually the all the multiplication and the loop operations are now part of main itself. There is no function fact1 being called here. So the whatever you see, the check for the loop termination, etc., is all happening here. So you can see the source code here, branch or not equal, and here is the multiplication operation with the for the which is basic for the factorial computation. So there is no function call here. Here is a recursive version of the factorial computation. So it's the same, similar to the iterative version, except that the implementation of the factorial is a recursive function which calls itself. Now we have set the same high level optimization and selected only the function inlining option. Let's see what kind of code gets generated. Let's compile it. So the build is done. Let's download it. So here is the main function. Interestingly, you see that it is very different from the iterative version, even at the main itself. So you can see that it is storing some register, preserving it, and then it is actually calling this function fact1. So branch with link fact1, and fact1 is basically doing the iterative, sorry, recursive version of factorial computation. We can execute and see. So it's going to factorial function where it is computing the multiplication. You can see the multiplication also here. So essentially, it is basically not optimize the function by inlining it. So there is a challenge to recursive functions being inlined. Of course, there are some compilers which are capable of doing. This being non-commercial version, uh, this is an evaluation version. Perhaps it's not supported, but there are most top of the line compilers can do it, but it is not an easy thing. So the point of this example is that the same function inlining may or may not work. The compiler's ability to inline will depend on whether it's having any recursion or other restrictions like the usage of globals and so on. Earlier, we talked about live variable analysis and aliasing. Let's now look at aliasing in more detail. So what is an alias? It's a variable, usually a global variable or a static variable being referenced and accessed via a pointer. Now, here is an example code, which basically is a character buffer pointing to a string hello. Basically, this function is using the global variable to clear that. Basically, it sets all the buffer values to be 0. Now, here is an alternative version, which basically is not doing that. It's actually calling, it's being called with a parameter, which is a character pointer, and it uses that pointer to initialize. So here the buff refers to this parameter, which is a character pointer, and the calling function would pass the global variable as the actual argument. So passing buffer as an argument removes aliasing, because aliasing with basically will introduce certain difficulties for the optimizer. So global in general, global variables are usually considered, it's a bad practice to use global variables. As much as possible, use local variables. Global can potentially be modified from anywhere in your program, so it may have unexpected results. They are scattered all over the code and so on. So this can result in complex dependencies, making it hard to understand the program and identify which part of the program might be affected if the value of the global is changed some elsewhere. From the optimizer's point of view, it's even worse. A store through a pointer can potentially change the value of any global variable, and therefore it is called aliasing. So it is aliasing when a variable can be accessed in more than its name. It's more than one way. Even though the programmer might know that the writing to the buffer, which this buff is pointing to, will never change the variable itself, the compiler has to assume the worst and reload the buffer from memory on every iteration of the loop. Passing the address of the buffer as an argument, this is the second version. Basically, instead of using the global variable, we'll remove the aliasing. So compiler can have difficulty with this kind of code. To avoid that, it is better to be explicit. Directly, it has side effect here, and then it may have difficulty understanding how it can be optimizing the load and store. Now, passing the address of the buffer as an argument instead of the global is better method. So after the small chain, the pointer buffer cannot be affected by the stores to the pointer. Basically, the pointer buffer is invariant in the loop. So basically, this becomes an invariant in the loop because it's pointed. In fact, it can be even a constant character star. Now, global variables can be useful when passing information between sections of the code that don't share a caller-callee relation. Otherwise, don't use the global variable. Use call with a pointer as an argument. So here is an example where there are two ways in which the function for clearing a buffer is called. So here is main, which calls clear buffer 1 and followed by clear buffer 2. Clear buffer 1 is directly accessing the global variable, and clear buffer 2 is getting an argument, which is basically a pointer to the same buffer. So it's basically called by main with the pointer to the global variable. and it is using this pointer as a reference for initializing it, just for distinguishing between this and this, a different value is being assigned. Now let's see what the generated code looks like. So here is basically, this is main. It initially calls clear buffer 1, and then subsequently it will call clear buffer 2. So here if we see clear buffer 1, here it is basically doing what you expect by loading the variable in a loop and storing the values, basically 0 here, um, and then incrementing for the loop, comparing for loop termination, and branching until the loop termination is satisfied. Finally, returning from this function. Now, this is not surprising. However, what is interesting is to see the alternate version, which is basically, you see there is no load and store here. Uh, Basically, this value constant 5a hexa is nothing but 90, and this is basically the loop index R1, and it calls a internal function which is basically memory memset function. So we can step into that. We can actually run up to this point. Now we can step into this. It is now calling this internal function, which is basically doing all the, as you can see, it is highly optimized in terms of the load and stores because it is using the function pointer here. Finally, the effect is same, but then the load and store accessing through the global variable through the pointer is much more efficient for the from optimization point of view. Well, the compiler, the optimizer can do many wonderful transformations. How you write your code can have a big impact because the compiler has to obey certain language specifications as well as basically ability to detect what your intent are. So very simple things when you follow can make a drastic difference. So here is a loop with basically the loop termination condition is a bit complex here. So you have certain array being accessed and the index of the array is being auto increment post incremented, and the value when the value of the array becomes 0, the loop terminates. Now the same thing can be accomplished in the source code by using a simpler condition. So the incrementing has been moved from the loop condition. It is explicitly incremented in the body of the loop. Now, logically they are same, but from an optimizer point of view, they are quite different. So if you look at it, basically this is nothing but this is the how it will be implemented. This is a pseudo code here, not the assembly code. So basically, this value of I is increment the operand, and then use it as a index to the array, compare the termination condition, and based on that either you stop the loop or go to the loop. On the other hand, this translates to basically if the end terminal condition is true, go to the no loop, otherwise increment. Now, how different is this? So if the value of I after the loop is irrelevant, it is better to place the increment inside the loop body. The second version can be executed without a temporary variable. So this temporary variable is not required here. The reason is that The C standard specification semantics of post increment states that the result of the postfix plus plus operator is the value of the operand. After the result is obtained, the value of the operand is incremented. So if you take I as the operand, plus plus is the operator. Now it requires the specification, language specification semantics requires that you first get the value of I and then increment that. So that means there is a temporary variable required here. So while it is fairly common that microcontrollers have an addressing mode that can increment a pointer after a load or store operation, very few microcontrollers can handle post increment of other types other than address types, which is non-pointer, with the same efficiency. So they need to use a temporary variable and do the increment. So to comply with the standard, the compiler may have to copy the operand to a temporary variable or a register before doing the increment. It is often better to split up, in general, complex expressions into several simpler expressions, because when the loop condition above was divided into a test and an increment, it became more efficient. So in general, it helps the optimizer not to have complex conditions inside a loop termination. Instead, you move it to the body. The compiler is capable of analyzing how to optimize these operations independent of the loop. So combining them confuses the compiler. To summarize what we have learned so far, trust the compiler. Modern compilers are based on significant theoretical foundations and are also based on decades of experience in generating code for different architectures. Hence, they are mature and bring a lot of productivity in terms of code optimization. As we saw earlier, the compiler applies not just one, but several optimization techniques in stages. Some are machine or architecture independent, and others are architecture specific. For example, if we were to do manually, at best we can think of a local optimization on a small section of code by handpicking the best instruction for the purpose on hand. This is called the peephole optimization, but the compiler can operate at both global and local optimizations. And it can and often will eliminate the part of the code entirely by applying a global optimization. For example, dead code removal or function inlining. With more sophisticated CPUs, with deeper pipelines, cache, and vectoring, it's almost impossible to hand optimize code. We also saw that sometimes when we write code apparently to optimize at the source code level, it may be counterproductive to the compiler optimization. This is typically the case with post-increment operations in general and inside loop termination conditions in particular. Having said that, it's still important that we check the compiler-generated code to see what transformations it has gone through and understand its logic. This serves two purposes. One, we can start seeing a pattern of correlation between our source code and its transformed version and develop the habit of coding to aid the compiler optimization. Two, there could be some scenarios where the compiler transformation may not be appropriate due to it being overly aggressive. For example, loop unrolling or function inlining can unduly increase the code size. In such situations, once we see the generated code, we can resort to controlling the optimization level using the compilation flag settings in the build scripts. A deeper understanding of the optimization techniques makes one a better embedded programmer. Have fun.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today